Hey y'all, my name is Aurod Ounsinegad, and I'm from Tarleton State University. Today for the TES competition, I'm going to be talking about the dynamics of the Eastern equine encephalitis infection rates, and I will be taking a mathematical approach. A little fun fact is that the background to this slide is actually the triple E virus. So a little bit of background to the virus is that it falls under the genus Alphavirus and under the family Togaviridae. It is considered an arthropod-borne virus, aka a arbovirus, meaning that it is spread by arthropods, meaning in our case, mosquitoes. So the virus is actually maintained at an endemic level between avians and mosquitoes. The viral life cycle of this virus actually begins in mosquitoes and makes its way through avians to a bridge vector to humans, or from avians to horses through fecal matter in water or feed. And that's the whole dynamic of triple E. Now, this mosquito in our model is actually the black-tailed mosquito, or more commonly known as Celaceta melanura. Now, signs and symptoms of triple E in humans include fever, headache, vomiting, diarrhea, and other neurological symptoms. These neurological symptoms only occur if the individual's central nervous system is shot. So this doesn't occur in all individuals. It typically tends to be in older individuals, as younger individuals have a better immune system and they aren't as immunocompromised. Of those who are infected and their central nervous system is shot, they have one of two ways of going. Either they go and they pass away within 1 to 2 weeks after the initial onset of symptoms, or they tend to have lifelong neurological or physical sequelae, such as brain dysfunction or severe intellectual impairment. Of these people, most of which tend to pass away within 2 to 3 years as their brain dysfunction becomes way too severe and they get termed as brain dead. Now, the most recent outbreak of triple E was actually back in 2019 with a total of 38 infections, 50% of which actually passed away soon after. Humans aren't actually the last host in this cycle. Horses are also considered another host in this cycle, as I mentioned previously. However, even though they do have the same symptoms as humans, they do die much quicker. Now, in our research, we're not really going to be focusing on horses. We're really just going to be focusing on the vector host transmission model. Now, this is going to be between the mosquito host and the passerine avian species that we are considering. Now, we are using an ordinary system of differential equations to gain insight on the dynamics of this virus. Now, here are our assumptions and our hypothesis. Our first bullet point shows the hypothesis that we made during our research. It really just states that the young of the year birds lack a sense of defense and they lack of the ability to leave the nest. This makes them a very, very easy host to target with the mosquitoes to target this host because it's not mobile. It can't move anywhere. It is stuck in its nest and it won't be able to move. And we assumed that the young of the year will actually make the reproduction number of the virus skyrocket more than any other parameter that we have included in our model. Beyond this, some other assumptions we made are that the young of the year have the same chance of getting bitten by mosquitoes as the adult counterpart. We assumed the avians are the only host for the black-tailed mosquito, and this is the only place that this black-tailed mosquito will take a blood meal, as it is ornithophilic. Now, the virus is also not transmitted vertically, meaning from mother to offspring. It can only be transmitted horizontally from birds to mosquitoes or vice versa. Now, mosquitoes also don't have a virulence for the virus, meaning a virus-induced death rate. They are infected and they're infected for life. They will never die due to the virus. They only die due to natural causes for whatever reason. Now, I created a flowchart to show what the flow of individuals between classes were and within our 9 classes in our differential equations that you will see on the next slide. Through this flowchart, you can see three big boxes. The one in the top left is the young of the year, the one in the top right is the adult birds, and the one in the bottom is the mosquitoes. Now, starting off with the top two, you have the adults and the young of the year. These two models are pretty much the same exact thing. The adults, the only part that the adults don't have that the young of the year do is the avian recruitment rate, or more commonly known as the birth rate. So you have a birth rate going into the susceptible class of young of the year, and you have a death rate coming out, and that death rate is coming out of every single class: susceptible, infected, and recovered. Now, between the classes, you see that you have an infection rate both in the young of the year model and in the adult model. Then in the infected class, you see that you also have a virulence coming out of it. This is the virus-induced death rate for both adults and young of the year. From infected to recovered, you obviously have your recovery rate, and out of your recovered class, you have your death rate. Now, for the mosquitoes, it's a bit different. You have your mosquito recruitment rate, or your birth rate. You have your mosquito death rate for each class, and you have the infection rate that goes from susceptible to your L class. Now, your L class is your latent period. So this class is used for the mosquitoes, as the mosquitoes cannot recover from the virus. And this latent period is just stating that the mosquitoes cannot infect other individuals. They can only lay in that latent class for a few days, in our case 3 days, until they make their way into the infected class through a multiplication of the incubation period times the number of latent mosquitoes. That shows the rate at which that transition between latent mosquitoes and infected mosquitoes is. Then you obviously have your mosquito death rate out of that infected class. Now, beyond that, if you take a step back, you see the bigger picture and the arrows that are within the flowchart between the boxes. In the top two boxes, you see that maturation rate that connects the two. This maturation rate just shows how quickly these young of the year birds are maturing from like the susceptible class to the susceptible class. So a young of the year to adults. They always go into their respective class. They never mature and go into a different class. That never happens. Then between the young of the year and adults and the mosquitoes, you see two different arrows, one going from mosquitoes to birds and one going from birds to mosquitoes. Now, the one going from birds to mosquitoes, you see you have an infectivity and you have an exposure coefficient. This shows how likely these mosquitoes are to successfully get a blood meal, which you see in the key is the feeding success, which is notified by number 1. And it shows you how infectious this bird is and how likely that mosquito is to be exposed to the virus. Now, going from mosquitoes to birds, you see you only have your exposure coefficient because it just shows how likely this bird is to get the virus. There's not really any other parameter that needs to be taken into account. Now, the number 2 in the model that you see is actually just the feeding success and the host preference. In our model, like I mentioned earlier, host preference is kind of just a 50-50. It's not really one is preferred over the other. It's kind of just the mosquito goes for whatever it chooses that day. But I thought to include it because it shows the dynamic better than if we didn't include it. Now, here are parameters and our ordinary differential equations. So on the left, you can see our system of 9 differential equations, and on the right, you can see the parameters that we have for all of them, the descriptions, and the parameter values. Now, we put these all together in order to get our flowchart and our model to work out, which you will see on the next slide. The flowchart pretty well signifies what each thing within each class does and how one individual goes from one class to the other and how infection really works. Now, in our results, you can see 3 graphs on the right-hand side of the screen. The top graph is the young of the year graph, the middle graph is the adult graph, and the bottom graph is the mosquito graph. Now, through this, we found that the reproduction number of the virus actually has to be less than or equal to 1 in order for the disease-free equilibrium to be locally asymptotically stable. If the reproduction number is ever above 1, the disease-free equilibrium is just thrown out the window and is not locally asymptotically stable. Now, we found that the avian birth rate is actually the most important parameter in our model because if it ever grows too high, then it has a potential of increasing that reproduction number. And as I mentioned earlier, that kind of just throws the model out of play, and it gives so many more individuals, in our case avians, the infection. Now, this actually proves our hypothesis because our hypothesis said that the young of the year have the greatest impact on our model. They would make the reproduction number skyrocket, and they would make the whole entire model go in and out of DFE, which actually did happen in our model because if that birth rate went above a certain number, then the model would be all thrown out of whack. Now, the infection actually only remains for 50 days. As you can see in the bottom model, you see that the infection in mosquitoes reaches a peak and it comes right back down. Around day 50, it dies out, and you can see that in the top two graphs, your susceptibles kind of plateau and your recovers also plateau within your adult class. You just see a straight line after about 50 days. Now, some future work that we have is that we want to create a second model that really demonstrates the dynamics between a bridge vector and the humans. It's just going to be like the avian host one that we have right now, but just with a little added spice, if you want to call it that. Now, we're going to only choose one bridge vector, which is just going to be a mosquito once again, and we're going to focus on host preference. So with this model that we made, we didn't really focus on host preference. But with the next model we choose to make, we want to focus on how dangerous this virus truly is to humans if the host preference, whether it's 50-50 or if it's 10-90, we want to know which preference is more dangerous. And we also want to focus on how many human casualties each parameter gives. Now, we also want to link the two transmission models together to find out the true dynamic of triple E, and we want to run mock trials and really analyze our data to make sure that the dynamic of our model is as correct as it can be. Here are my references. Thank you very much. Any questions?